Hi everyone, we are Nguyen Viet Tien, Dinh Nguyen and Pham Phuong from the Faculty of Data Science and Artificial Intelligence at National Economics University. Today, we are honored to present our comprehensive report on memory management in x86-64 architecture. This video presents an in-depth analysis of memory management mechanisms in the x86-64 architecture, a foundational component of modern computing systems. We will begin by outlining the key features of x86-64, then clarify the distinction between virtual and physical memory, and explain how the operating system manages these. Next, we will dive into the paging mechanism, including the four-level page table structure and the breakdown of the 48-bit virtual address. We will also discuss physical address extension, PAE, page sizes, page table entry flags, access control, the no-execute, NX, bit, and the role of the translation look-aside buffer, TLB. Throughout, we aim to combine theoretical explanation with illustrative examples to provide a clear understanding of how memory is managed in x86-64, and why these mechanisms are crucial for system performance, security, and scalability. Let us begin by laying the foundation for our discussion, understanding the x86-64 architecture and the importance of memory management within it. Overview of x86-64 architecture. x86-64, also called AMD64 or Intel 64, is a 64-bit extension of the x86 instruction set. It improves system performance by expanding memory capabilities, adding 64-bit registers, and supporting large address spaces, up to 256 TB virtual and 4 PB physical. It runs both 32-bit and 64-bit applications and includes advanced instruction sets and four-level paging for efficient memory management. Role of memory management. Memory management ensures system stability and performance by isolating processes, managing memory usage, and enabling address translation. It allows for memory sharing, swapping inactive pages to disk, and enforcing access control with features like the NX bit to prevent unauthorized code execution. Importance of virtual memory. Virtual memory isolates processes, making them secure and efficient by allowing them to access seemingly continuous memory, even when it's physically scattered. It also enables large applications to run without exceeding RAM capacity by using disk storage. This improves stability by preventing one process from crashing the whole system, and shared libraries help save resources. The multi-level paging system efficiently translates virtual addresses to physical ones. Purpose and scope of the report. This report explains memory management in x86-64, covering topics like virtual versus physical memory, paging, page table entries, and advanced features like PAE and TLBs. It also highlights security and performance improvements in modern memory systems. With this foundation, let's move on to our next chapter, where we will explore the crucial distinction between virtual and physical memory, and the operating system's role in managing them. With this foundation, let's move on to our next chapter, where we will explore the crucial distinction between virtual and physical memory, and the operating system's role in managing them. Having established the background and motivation for memory management, we will now clarify the difference between virtual and physical memory, and explain how the operating system bridges the gap between them. Virtual memory is an abstraction layer that allows the operating system to present each process with a large, continuous address space. In reality, the operating system maps these virtual addresses to physical memory, RAM, or disk storage as needed. In x86-64, the architecture supports 48-bit virtual memory addresses in current implementations, enabling processes to access up to 256 TB of addressable space. This approach enhances memory protection, extends address capabilities, and optimizes program memory handling. Physical memory refers to the actual hardware, RAM, installed in the computer system. It is the finite pool of memory that the operating system manages and allocates to active processes, the kernel, and hardware devices. Physical memory is limited by hardware constraints, so it must be managed carefully to avoid excessive system loading and fragmentation. The paging system converts virtual memory addresses into memory addresses that the CPU uses for memory access. The operating system manages the mapping between virtual and physical memory using key mechanisms, page tables, map virtual addresses to physical memory. Memory allocation assigns memory to processes. Swapping and paging moves inactive pages to disk when RAM is full. Access control enforces permissions via page table flags. These features allow for multitasking, memory protection, and efficient use of system resources. Virtual memory offers key benefits that boost system efficiency, security, and flexibility. Process isolation keeps programs from interfering with each other. Better RAM usage allows more apps to run by loading only needed parts. Simplified programming. Developers work with large, flat memory spaces. Overcommitment allocates more memory than physically available using paging. Security. Features like the NX bit prevent unauthorized code execution. Crash containment. One process can't crash the whole system. With a clear understanding of virtual and physical memory, we now turn to the heart of memory management in x86-64, the paging mechanism. Paging splits both virtual and physical memory into equal-sized chunks. We call them pages for the virtual memory, frames for the physical memory. When a process runs, its pages are loaded into available frames from the disk. This method helps reduce memory fragmentation, simplifies swapping data, and allows multiple processes to run, even if there's limited physical memory. For x86-64, the virtual address is 64 bits, but only the lower 48 bits are used, giving us 256 TB of virtual address space. The virtual address is divided like this: 9 bits for each of the 4 page table levels, PML4, PDPT, PD, and PT. 12 bits for the offset within the page. This setup makes it easier to map virtual addresses to physical ones. The x86-64 architecture uses a 4-level page table, which includes PML4, PDPT, PD, and PT. Each level points to the next, eventually mapping virtual addresses to physical memory. This system reduces memory overhead and speeds up address translation. Each page table entry contains the physical address of the frame or next level. Flags for permissions like read, write, user, supervisor, and NX, no execute. These details are crucial for security and performance. With a solid understanding of paging, we can now examine how x86-64 extends its addressing capabilities even further through physical address extension, or PAE. Having explored the paging mechanism, let's see how x86-64 overcomes traditional memory limits with physical address extension. PAE, physical address extension, allows 32-bit systems to access more than 4 GB of RAM. In 64-bit mode, PAE extends the physical address size to 52 bits, enabling up to 4 PB of RAM. This is vital for modern applications like databases and virtualization that require large memory spaces. With PAE, the physical address can go up to 52 bits, significantly increasing how much memory can be addressed. This lets systems handle larger workloads and datasets. Larger address spaces mean more complex page tables, which need more memory to store. However, the benefits of supporting large applications and datasets outweigh these costs. Operating systems must optimize these large tables using techniques like large pages and TLB optimization. As we consider the impact of expanded address spaces, let's focus on the different page sizes supported by x86-64 and their optimization. The default page size in x86-64 is 4 KB. This size strikes a balance between efficient memory usage and manageable page table size. x86-64 supports large pages, 2 MB pages through page directory entries, 1 GB pages through page directory pointer entries. They're great for memory-heavy tasks like databases and virtual machines, boosting performance by reducing page table overhead. Use cases for different page sizes. 4 kilobytes pages are for general apps and OS code. 2 megabytes and 1 gigabyte pages are best for high-performance computing and large databases. Choosing the right page size helps optimize performance and memory use. Of course, managing memory isn't just about size, it's also about security and access control. That brings us to our next chapter, page table entry flags and protection mechanisms. Now that we've discussed page sizes, let's examine how x86-64 ensures memory security and control through page table entry flags. Present, read, write, and user, supervisor flags. Page table entries have important flags for memory access control. The present, P, flag indicates if the page is in memory, while the read, write, R, W, flag determines if the page can be modified. The user, supervisor, U, S, flag controls access, allowing either user mode or kernel mode access. These flags ensure memory protection. NX, no execute, bit and its security role. The NX bit enhances security by preventing code execution from certain memory pages, protecting against attacks like buffer overflows. Accessed, dirty bits and memory management. Additionally, the access bit tracks if a page has been read or written, and the dirty bit marks pages that need to be saved to disk if swapped out. These bits help manage memory efficiently and optimize paging. Efficient address translation is critical for system performance, which leads us to the next essential component, the translation look-aside buffer, or TLB. Having established how access is controlled, let's look at how address translation is accelerated in x86-64 systems using the TLB. Function of the TLB. The TLB is a specialized cache that stores recent virtual to physical address translations, speeding up memory access by reducing the need to warp the page tables for each memory access. TLB miss and page table walk. When a translation is not found in the TLB, a TLB miss, the CPU must warp the page tables, which is slower. Minimizing TLB misses is crucial for maintaining good performance. TLB levels and optimization techniques. Modern CPUs use multiple levels of TLBs, with separate caches for instruction and data. Techniques like large pages and prefetching help reduce TLB misses and optimize memory performance. With these mechanisms in place, x86-64 achieves significant advantages in security, performance, and scalability. Let's summarize these benefits in our final chapter. To conclude our technical discussion, let's highlight the key advantages that x86-64's memory management brings to modern computing. Security features. Process isolation ensures each process has its own address space, preventing interference. Privilege levels restrict access to sensitive memory, while the NX bit blocks code execution from data pages, protecting against exploits. Performance gains through paging. Paging optimizes memory usage, allowing systems to handle applications and datasets larger than physical memory. Scalability of memory. x86-64 supports up to 256 TB of virtual memory and 4 PB of physical memory, with room to grow as hardware evolves. Compatibility and flexibility. The architecture supports both 32-bit and 64-bit applications, offering flexible memory management for diverse environments, from desktops to high-performance computing. Having reviewed these advantages, we're ready to wrap up with our overall conclusions and takeaways. In summary, memory management in x86-64 architecture is the backbone of modern operating systems, providing the foundation for security, performance, and scalability. A deep understanding of these mechanisms is crucial for anyone working in computer science, data science, or IT. Thank you for your attention. We welcome any questions or feedback.